code on this computer. So we're going to go through the stuff on the course website, which is week 2. So let me show you. Share screen, course website. This one. So I'm going to go through this stuff as quickly as possible. I hope all of you have looked. I mean, I asked you guys to go through the week 2 videos. Had you done it or not? I mean, had you gone through the week 2 videos? There are only 4 videos. There's one on summary statistics. There's one on graphical displays, one on the normal distribution, and the one on binomial distribution, right? So I hope all of you have looked through these 4 videos, right? So what I will do now is to go through those 4 videos as quickly as possible, and then I will do some examples. Okay. Now, before I start, I'd like to make an announcement. Last week, which was week 1, I mean, all the videos from this session, from whether it's a review session or whether it's a tutorial session, are in this website, right? So you can see the videos for the review session, these 2, and the videos for the tutorials are over here. So you should be able to see them soon after the sessions. You should be able to see the videos, right? So I don't use Blackboard. I don't use Blackboard to post my videos. So all the videos from every session posted, all the videos from every session is posted on this website, which is the one I'm talking about, is minerva.it.manchester.ac.uk, right? This website contains all the videos you need to know, right? All right, guys, now let's begin. All right, let me change the camera now. Here we go. Stop share. Element all. I want to change the camera. Excuse me, sometimes I get into trouble changing the camera. All right, can you see it now? Hello, guys. Well, there's some problem. All right, guys, can you? Yeah, it's a bit. Should be better now, I think. I hope you can see it. Oh, sure. I'm trying to focus it. Okay, I think it's better now. Okay, right. Okay, the first thing I want to do is to talk about summary statistics. If you're given a data set like this, the first thing you need to know are order statistics. Order statistics are simply data arranged from the smallest to the largest. So this is the smallest, this is the largest. This is the sample mean. I'm sure all of you know the sample mean is simply the average of the data. This is the sample median, defined depending on whether the sample size is odd or integer, is defined differently. Okay. And this is the sample Pith quartile or quantile, is defined by this expression here. This is the definition of the Pith quantile or quartile, where P is a number between 0 and 1. Where R prime is the integer part of this, R is given by this, right? And if R prime is 0, then the Pith quartile is the smallest data point. If R prime is N, then the Pith quartile is the largest data point, right? I hope you guys look through this video, so I'm not going to spend time going through the examples. So the first quartile or the first quantile is the Q at 0.25. That is when P is equal to 0.25. The third quartile is when P is equal to 0.75. Now, the quantile or quartile is formally defined by this equation here. So for example, the Pith quantile or quartile is the value for which the CDF at Q of P is equal to P, right? Now, the sample variance, I think I talked about this last week. There are two definitions. This is the biased version. This is the unbiased version. Normally, people use this unbiased version, which is the common, right? Which is the common, excuse me, I'm trying to, oh, here we go. Just a minute, give me a sec, guys. All right, and there are alternative formulas for the sample variance, and this is the alternative formula for the sample variance when it's biased, and this is the alternative formula when it's unbiased, right? Okay, my cursor is not moving. Why is this? All right, and the sample standard deviation is the square root of the sample variance, and is defined by one of these two, depending on whether the sample, whether this is the biased version and this is the unbiased version, right? And the sample range is the difference between the largest and the smallest data points. And the sample interquartile range, or IQR for short, is the difference between the third quartile and the first quartile, right? And these are R commands for computing. These are R commands for computing. Excuse me. I'm unable to move my cursor for some reason. These are R. So, for example, the R command for computing the order statistics is this one. This is the R command for the mean, sample mean. The R command for sample median. And this is the R command for the Pith quantile or quartile. And this is the R command for the first quartile, the third quartile, and so on. And this is the R command for the sample variance, the R command for standard deviation, sample range, and this is the sample interquartile range, right? Okay, these are some examples. I hope you looked at these examples. So I'm not going to go through them. These are some more examples, right? These are some more examples I did. This is the proof of star. Star is basically the equation that I showed you earlier. Let me show you one more time if you haven't noticed it. This equation here is star, right? Okay. Excuse me, just a minute. I'm still trying to admit the people who are late. Just give me a sec, guys. Just give me 1 minute, okay? Hello, guys. The proofs are, yeah, they may be examinable. Okay, thank you, guys. So this is a star that I showed you earlier. So the proof here is this is the proof of star, right? Which I hope you guys look through it. I hope you guys look through this proof. If you have any questions on the proof, please let me know, right? And this is the proof of double star. Double star is another thing that I talked about earlier. Let me show you. Double star is this one I talked about earlier. The double star is this one, which I mentioned earlier, right? Okay, so this is the proof of double star. Again, I expect you to know these proofs, right? Okay. And this is the proof of triple star. Triple star is, one more time, I mentioned what triple star is this one, right? Okay. So this is the proof of triple star. So again, I want you to know, go through this and make sure that you understand the proofs, right? And the next section is on graphical displays. The next section is on there are 3 graphical displays. The first one is the box plot. The box plot, it looks something like this. I hope you can, I'm not sure whether it's clear enough or not. All right, in the box plot, I will explain what they are in a minute. Right, I'll explain. Oh, okay, guys, sorry for the delay. I'm having problems with the computer. Box plot, I will explain what they are in a second. The middle line is the median. The bottom line here is the first quartile, which I explained to you a minute ago. This line here is the third quartile, Q 0.75. And this line here, the distance between this line and this line is 1.5 times IQR, right? And the distance between this line and this line is again 1.5 times IQR. IQR is the interquartile range I talked about a few minutes ago. Right now, if you have any data that falls below this line or above this line, then what you have is an outlier, right? So for example, if X is greater than this point, which is this bar here, or less than this, which is this bar here, then X is referred to as an outlier. And the R command for an outlier is box plot in brackets X, right? All right, this is a bar plot. Like when you have data on parties, like 5 different parties, we talked about it last week, you can use a bar plot, right? The R command is bar plot in X. The box, what the box shows is the box basically shows the variability of the data. So the longer the box, the more variable the data is, right? So in this case, and also it also shows like whether the median is halfway in between the two quartiles. If it is so, then the distribution is symmetric, right? And this is a histogram. This is a histogram, and you use the command hist in brackets X. I will do an example on this later on if I have time. And if the histogram is symmetric, if it is symmetric like this, then the distribution is symmetric, right? Whereas if the histogram is kind of skewed, like if it is skewed like this, then you have a skewed distribution. Like if the histogram is skewed to this way, then it's known as, what you have is known as a positively skewed distribution. And if it is skewed to this way, then it's known as a negatively skewed distribution. Yes, you're right, Charles. Yeah, if smaller the IQR, the smaller the variance, right? IQR is a measure of variability, so is the variance. Yeah, and the middle line median is kind of tells you whether the distribution is symmetric or not. So if the middle line is halfway between the third and the first quartile, then the distribution is kind of symmetric. All right, the next chapter is on normal distribution. It's also known as the Gaussian distribution. You might have covered this in probability 1. This is the density of the normal. This is the CDF of the normal, where phi denotes the CDF of N01, right? And this is a property of a CDF. These are some examples on how to read the normal table, right? I hope all of you guys watched the video, right? And okay, and this is the normal table. If you watch the video, I explained there how to read the table, this table here, right? And this is the command for computing the density of a normal distribution, and this is the command for computing the CDF of a normal distribution, right? And these are some properties of the normal distribution. So the mean is mu. This is the variance. This is the standard deviation. If you have two independent random normal variables, then their linear combination is also normal, right? And once again, if you have n independent normal variables, then their linear combination is also normal, right? Okay, guys. So these, yeah, you are right, Robert. The range is also measure variability. Range is the maximum minus the minimum, right? And one more property, if you have IID, independent and identical normal variables, then their sample mean is also normal, right? And if you have, the final property is that if you have a normal random variable, then this one is known as a scaled version. This is known as a scaled version of a normal variable and has the standard normal distribution, right? Okay, and this is the sample mean. The sample mean of a sequence of IID is also normal, right? Okay, right. Finally, the estimation. If you have a data set from a normal distribution, then the two parameters mu and sigma can be estimated as follows. So estimate for mu is the sample mean. The estimate for sigma squared is given by the biased version of the sample variance. Remember, this has n in place of n minus 1, right? Okay, these are some examples. I hope you watched the videos to follow these examples. Right, the final thing is about the binomial distribution. The binomial distribution has the PMF given by this formula here, right? Where I'm sure you're familiar with this. So this is the PMF, and the CDF of a binomial is given by this expression here, right? Okay. And two properties, I'm sure you're familiar with these properties. The expectation is m times p. The variance is mp times 1 minus p. This is the R commands. This command computes the PMF of a binomial, and this command computes the CDF of a binomial, right? Now, if you have a data set from a binomial distribution with the parameter m known, but p is unknown, then the p can be estimated using this formula here, right? Okay, this some example 1 on binomial, which should be easy for you guys. Example 2 on binomial, example 3 on binomial, and here we are trying to compute this probability for a variable x following this distribution. Now you come up with this summation here, which is difficult to compute even with the computer, right? And next week, there's week 3, I will show you how to compute this, right? If you haven't watched the stuff for week 3, I will show you how to do it, how to compute complicated sums like this, right? Using a tool called central limit theorem, which I will talk about in week 3. Right, okay, all right, so this is stuff. And so I just went through this quickly because I need time to do examples, right? I need time to do to do some examples. That's why I went through this so quickly. All right, let me start with some examples. Do you guys have any questions so far on the stuff I did? Any questions? Feel free to write to me. Okay, example 1. Example 1. I hope you can see this, guys. All right, suppose I already have it written here. Sorry, excuse me. Okay, this is example 1. I have written it here. So the question is, compute the summary statistics for the following data. All right, the first thing you need to do is to order the data. Order the data as follows, right? So the smallest value is 0. The second smallest is 1. The third smallest is 2. The largest is 3, right? So the mean, the sample mean, the sample mean is just the sum of these numbers divided by 4. 4 is the number of data, right? So you will get this to be equal to 1.5. And the sample median is, because you need to pick up the 2 middle numbers, which are 1 and 2, and take their average. So it's 1 plus 2, because you have 4 numbers, right? 4 is an even number. So you need to pick the 2 middle numbers and take their average. So that will give you 1.5. So you see the sample mean and the median are equal. Now to compute the first quartile, the next thing is we want to compute the first quartile, right? To compute this, you use the formula that I gave you a while ago, right? So if you use you need to use the formula. So first you need to use R prime. R prime is P times N plus 1, which is 0.25 multiplied by 4 plus 1, right? Which is 1.25. The integer part of 1.25 is 1. All right, so using the formula that I gave you a few minutes ago, you will get this, right? And this will be equal to x1 is the smallest data, which is 0. 1.25 minus 1 is 0.25 multiplied by x2 is 1 minus 0. So the first quartile is 0.25. Okay. And the next thing I want to find is the third quartile, right? So for this, R prime is gonna be P, which is 0.75 times N plus 1, 4 plus 1. And this is gonna be the integer part of 3.75, which is 3, right? So if you use the formula that I gave you earlier, this is gonna be x3, the third smallest data, plus 3.75 minus 3. Then you have x for, okay. So this, if you compute this, guys, this will be equal to 2.75. So this is the third quartile, and this is the first quartile. Now the next thing we want to compute is the sample variance, Right, sample variance, there are two different formulas. The first formula I'm going to use is the unbiased formula. So if you use, it's going to be n minus 1, which is 4 minus 1, right? Then in brackets, you have 1, excuse me. 1 is the first data, 1 minus 1.5. 1.5 is the sample mean. Yeah. Right, this is what you get. Right, and if you compute this, guys, using a calculator, if you have one, this will be 1.666667. This is for the unbiased version. This is unbiased version. For the biased version, right, for the biased version, you will get, you do the same thing, but this time you divide by 4, right, not 4 minus 1 of the same thing. And this will give you 1.25. This is the biased version of the sample variance, right? Now, okay, right, this is the, we're not done with that yet. All right, the next thing is, excuse me, the next thing we need to compute is the sample standard deviations, so SD. SD stands for standard deviation. So standard deviation is simply the square root of the sample variance. So this is 1.66667, the square root of it for the unbiased version, right? And equal to the square root of 1.25 for the biased version, right? And the next thing we need to compute is the range. Remember, the range is the difference between the smallest and the largest data. So in this case is X4 is the largest data, X1 is the smallest data. I cannot hear anything. Can you guys hear me, guys? Hello. Everybody can hear except one person. I don't know who it is. Hello. Okay, guys, so the range is the smallest data, which is the largest data is 3, the smallest is 0. Can you check your mic, madam? Your microphone. So the range is equal to 3. And IQR is interquartile range, which is the difference between Q 0.75 and Q 0.25, right? Now, these two we computed earlier. This one turned out to be 2.75. So 2.75, take away 0.25, which is 2.5, yeah? All right, so this completes the summary statistics, right? So I computed basically everything that we talked about, the sample mean. So I computed the sample mean, the sample median, first quartile, third quartile, the sample variance, the sample standard deviation, the sample range, and the interquartile range, right? So this completes example 1. The next example I'm going to do is example 2. Example 2 is the following. Right? Draw a histogram for the following data with interval width equal to 0.5. So you got this data. And we want to draw a histogram. I mean, excuse me, I got a problem with the cursor one more time. All right. So the first thing you must do is to have the interval. You need to define a column for the interval, and you need to define a column for the frequency. we want the interval to be of length 0.5. So you can have -2 to -1.5. This is one possible interval. So I'm defining, as you can see, I'm defining the intervals. All right, so these are the intervals. And the next thing I'm going to do, is to count how many of the data points fall within each of these intervals, right? Okay. I'm having trouble. All right, for the frequency, for the first interval, you have only one data point. For the second interval, you have one. For the third interval, you have two. And for the fourth interval, you have 0. For the fifth interval, you have 3 data points. The next one is 2, and the next one is 1. So this should add up to 10. You see, we have 10 data points in total, right? Okay, so the next thing you should do is, to plot frequency versus interval. And if you do that, this is what you will get. So you see, I hope you can see this. Yeah, I'm trying to invite the student back, but I've got problems with moving my cursor. I don't know what the problem is. I've got a problem with my computer. I don't know why you guys come late, but all right. So this is what you will get. You should plot the frequency versus the interval, right? So frequency. This is the frequency column, and this is the interval column. This is what you will get, right? Next, now sometimes we want, instead of plotting the frequency, we want to have this in a density format, right? We want to have this as density, not frequency, right? So to do that, you need to define a third column, which is called density. All right. All right. And the density is defined as follows. The density is defined as the frequency divided by n. N is the total number of data points, which is 10, times the interval width. Right, so in this case, this is frequency uh, 10 times the interval width is 0.5, right? So 10 times 0.5 is 5, right? So the density is 1 divided by 5, 1 divided by 5, 2 divided by 5, 0, 3 divided by 5, 2 divided by 5, and 1 divided by 5. And all this should add up to 1, as they should, right? Okay. Okay, now you should plot. Yes, you're right. The 10 denotes the total number of data points, which is n here. N is the number of data points, right? Okay, so you should plot the density column versus the interval column. This is what you will get, right? So here on the y-axis you have the density, and on the x-axis you have the width, right? And all the area below this, all the area underneath underneath this density must be equal to 1, right? This area here, all this area, right? If you compute the area below this, it should add up to 1, right? No, they should add up to 1, Vincent. How do you get 2? I mean, the probability distribution should add up to 1. I mean, you should. Okay, right, okay. Right, so that's example 2. The next example I want to do is example 3, right? I hope you can see this. So in this example, I want to show you how to draw a box plot, right? Now for a box plot, as you may know, we need to compute the quantiles, right? Now it can be shown if you use the formulas that I gave you earlier, right? It can be shown that the median for this data, the median is equal to 0.17, right? And Q at 0.25 is minus 0.825, and Q at 0.75 is 0.97, and therefore IQR is the difference between these two numbers, right? Is 1.795, and so all this you can compute using the formula that I gave you earlier, right? Okay. Okay, so if you compute them, and then the next thing you need to compute is this: Q at 0.25 minus 1.5 times IQR, right? And this turns out to be minus 3.5175. And so this gives you the lower fence, right? And the next thing is Q at 0.75 plus 1.5 times IQR. And this gives you the upper fence, which is 3.6625, right? All right, so these are all the numbers that we need in order to draw the box plot. Now, if you draw the box plot, this is what you will see. I hope you can see this. I hope you can see this, guys, that the box plot looks like this. Now, this is the median. The median is the middle line, which is, according to my calculations, is equal to, can you see this? It's equal to 0.17. So this is this point here is 0.17, right? And this guy here is the Q at 0.25, which is minus 0.825. And this guy here is the Q at 0.75, which according to my calculations is 0.97, okay? Right, and this, and then you have this, right, let me show you. Then you have this guy here, which is the lower fence, and this is the upper fence. So this is around minus 3.5. So minus 3.5 will be like way below. It will be somewhere like here. I don't know if you can see this here. So this is, I think minus 3.5 will be this one, around minus 3.5. This is the lower fence. the upper fence is this one, 3.6625, and that will be way above somewhere here. So this will be 3.6625, right? This is the upper fence, right? And this guy here is minus 3.5175, right? Now, let me explain to you what these two lines are. These two are not the lower fence or the upper fence. What this line here is known as the lower adjacent, or this is known as the lower adjacent, right? Okay, and this line here is known as the upper adjacent. Okay, it's known as the upper adjacent. The lower adjacent, I haven't explained this in the videos, but let me explain what they actually mean, right? The lower adjacent is defined as the following, right? Is the smallest. Right, the lower adjacent is defined as the smallest data value, right? That is greater than the lower fence, which is minus 3.5175. The lower fence, I already defined what they actually mean. The lower fence is, guys, this one. Remember, I mentioned this to you. This is the lower fence. The lower fence is defined by this value here. And this value here defines the upper fence. I mentioned this in the video. I don't know whether you recall. This is known as the upper fence. So the lower fence is minus 3.5175. The upper fence is 3.6625, which I have plotted here. So this is your lower fence, right? And this is the upper fence, 3.6625, right? Okay, now I'm defining what this line here is known as the lower adjacent, and it's defined as the smallest data value that is greater than the lower fence. And this guy here is known as the upper adjacent, and is defined as the excuse me, just a minute, just give me a second. And this is defined as the right. The upper adjacent is defined as the largest data value that is less than the upper fence. The upper fence is this one here, 3.6625, right? So if you look at the data, you should go back to the data set, right? This is the data that we are given. And if you're looking for the largest data value that is less than 3.6625 and is clearly equal to this one here. This is the largest value in the data that is less than 3.6625. So the upper adjacent, which is this point here, must be equal to 1.10, right? And if you go back to the lower adjacent, remember the lower adjacent is the smallest data that is greater than the lower fence. The lower fence is minus 3.5175. Okay, all right, and the smallest data that is greater than the minus 3.5175. If you look at over here, is minus 1.80. So this value here is minus 1.880, right? So this is the box plot. I mean, I hope you're okay with this. I mean, I know it looks kind of complicated, but it's not really. I mean, so basically you need, in order to draw a box plot, you need to have the median, which is the middle line, the first quartile, which is this one, the third quartile, and then the upper fence, which is this one, and then the lower fence, which is this one. And then finally, you need to determine the upper adjacent as the largest data that is less than the upper fence, and the lower adjacent, which is the smallest data that is greater than the lower fence, right? This is all you need to draw a box plot, right? So I hope you guys got, I hope you followed this. Yeah, you can draw a box plot horizontally too, right? You can draw a box plot horizontally too. But I think the vertical one is, I don't know, they are both the same, I guess. They don't make a lot of difference. I mean, right? They are both the same. So this is there are basically 1, 2, 3, 4, 5, 6, 7 points you need to work out in order to draw a box plot. You need to work out 7 different values. The first one is the median, the middle one. The second one is the first quartile, or Q at 0.25, Q at 0.75. Then the lower fence, which is defined as, I told you what the definition is. I mean, the lower fence is defined by this formula here. So the Q at 0.25 minus 1.5 times IQR. This is the lower fence. The upper fence is defined as Q at 0.75 plus 1.5 times IQR, right? That you need to work out, right? Then finally, you need to work out the lower adjacent, which is as the smallest data that is greater than the lower fence, and the upper adjacent, which is the largest data that is less than the upper fence. All right, guys. So that completes example 3. Unless you have any questions on the 3 examples I've done so far, or no? Any questions, guys? For the histogram, is the density the same as the frequency density? What do you mean? I don't understand. For the histogram, there are 2 different things. There is one. What do you mean, John? I mean, do you mean there are 2? You can have the frequency like, right? This is, excuse me. This is the density version of the histogram, and this is the frequency version of the histogram, right? So in the frequency version, you just plot the frequency versus the interval width, right? And in the density version, you plot the density versus the the frequency width, right? Okay. All right. Now, when you plot the density, the density is computed like using this formula here. This is the formula you need to. This is yeah, you're right. Frequency density is frequency density is another name for the density. For computing the density, you need to use this formula. It's the frequency divided by the total number of data points multiplied by the length of each interval, right? All right. So that's what I have written down here, guys. So this is the frequency divided by 10. 10 is the number of data points, and the interval width is 0.5. All right. So 10 times 0.5 is 5. Yeah. Okay. So that's what I have written here. Okay. So you see what the difference is. They both have the same shape. I mean, both of them have the same shape. They kind of tell you that it looks kind of like a normal distribution. I mean, approximately it looks like a normal distribution, right? Okay, so that's how you do the histogram, right? Any other questions, guys? Now, one other thing I wanted to do, I know I still have time. One other thing I wanted to do, but I don't think I will have time to complete it, is the following. This is example 4. Example 4, okay? Suppose right, this is, I don't think I will have the time to finish this example. I mean, I only have 6 minutes left. The way to do this example is, I mean, the problem here is to show that the expected value of the sample variance, this is the unbiased, remember, this is the unbiased version of the sample variance, is equal to sigma squared, which is the population variance, right? Okay, so now in order to prove this, you need to first show that the, okay, let me give you a hint. I mean, I don't expect you to do this, but I mean, maybe some of you can try to do this. That the first thing you need to show is that S squared Right, write it like this, right? Okay, and then IID means independent and identically distributed. For instance, IID means independently and identically distributed, right? Okay, write this guy as this, right? And then expand this. If you expand this, you will get 3 different terms, right? This, you get 3 different terms, right? It's like a plus b squared is a squared plus b squared plus 2ab. And then you take the sum inside. Okay. All right, and then, all right, then you can simplify things a bit. Because this is a constant, doesn't involve any I. The sum of a constant is n times the constant, right? So this will be right, and because this guy here is a constant, this guy here is a constant, right? Doesn't, right? With respect to I, you can pull it outside of the summation, right? Okay, so you can write this as 2 times okay, like this, right? Okay, the next thing you need to do is well, I'm nearly running out of time, so I will the next thing you need to do is to take this sum inside the brackets, right? And you will see if you take the summation inside the brackets, you will get the following. You will get n times x bar minus mu. Right, this is what you will get. Right, these two are the same except for the minus, so this will be all right. So you get to this stage, right? And the next thing you need to do is to take the expectation of x squared. Now, if you take the expectation of x squared, this will be 1 over n minus 1. Excuse me, guys, I'm running out of time, but times this minus n times the expectation of this. Okay, Now, this guy here, I will explain Sakin. Yeah, Sakin. I will explain why that in a minute, but if I have time. But let me finish this first, right? This guy here is the variance of xi, which is sigma squared. So this becomes sum of sigma squared. And what you have here is the variance of x bar, which is sigma squared by n. All right. So this is 1 over n minus 1 times n minus 1 sigma squared, which is sigma squared. I kind of rushed it a bit because of the time. So I hope you followed this, but I don't expect you to know this proof for the exam or for any other assessment. But if you did not follow this, just give me a email or call me or Zoom me or whatever. I will try to explain this in more detail later on, right? But this is the proof. This is the proof that the expectation of the sample variance is equal to sigma squared, right? Okay. Right, I'll see you guys in a sec because there's a tutorial starting at 11 a.m. That's in about 10 minutes time. So I'll see you guys shortly, okay? Bye.
Thank you.
Have a good day.
Go here. Come, quickly. It's moving. It's not moving at all. Huh? Where is it?
Yeah. No problem, bro. Is it recording?
I need to close.
What?
I can't close it without pointing over here. I need another class starting now, 11. Is it 11 already?
Yeah, 11. 11:04. சும்மா அழாதேப்பா போடு. இதை வந்துட்டு அது நீங்க துடைச்ச வழியா தான்
Meeting all.